Good afternoon to everyone. Thank you for coming to this talk. I also would like to take advantage of this opportunity to thank to the members of the jury for taking the time to read this manuscript and provide feedback on this research. Before starting, I also would like to acknowledge the SPEED project, which was the project that provided funding for this research via the CNRS and the next team. So today I'm going to present the results of 3 years of research in the domain of traffic networks, in particular estimation and predictions techniques applied on these networks. So let me first introduce the main motivations of the problem and the motivations that led to this research. So as cities pursue the career towards urbanization, the development of traffic infrastructures doesn't grow at the same rate. And one example of this situation was found by INRIX, which is an enterprise in charge of collecting data of these characteristics, in which in 2014 they reported France as part of the list of the most congested countries. For example, in Grenoble, drivers spent in average 33 hours in congestions a year, being the worst hour Fridays in between 5 and 6. And even though the position has changed along the years, it's not very clear how it evolves. So the situation reveals how important is provide estimation of congestion and estimation of the state of the road as a useful tool for multiple users such as drivers, commuters, and authorities in charge of managing the highways. And in addition, we can add value to this proposition by proactively predicting the evolution of traffic conditions, and this evolution can contribute to the state of the network. And moreover, one way to tackle the problem is to proactively predict the evolution of traffic condition and provide information to the user. So first, I'd like to provide a brief recall on the modeling and the estimation problem. And everything starts from the real world, where multiple systems coexist, in this case a traffic road. In this case, the reality can be analyzed from two complementary frameworks. The first one, the modeling framework, in which mathematical abstractions can explain the system behavior. And with the help of theoretical tools and laptops and computers, we are able to simulate and establish the behavior of the system. In a complement to this problem, by installing sensors in the real system, we can collect information that can complement the behavior captured by the abstraction, and the estimation theory is the way that we can use in order to fuse this information and obtain a more complete understanding of the reality. In order to solve this estimation problem and the prediction problem, which consists in estimate values in the future time, we can proceed in this way. So from the actual traffic condition, we collect two main elements. The first one, the data element, which we can group at historical level or real-time level. And in addition, we consider a second element, which is a model, a traffic model, which regularly is developed from traffic flow theory. Historical data can be used to train parameters and define characteristics of a family of models, which are called data-driven. Meanwhile, real-time data can fit these models in order to provide the current traffic conditions. In addition, on the other approach, we can establish estimation techniques that are model-based, and they consider in multiple ways the input of data. So historical data can be used to calibrate parameters of this model. This data can be also integrated into the model in a way of observations, and the real-time data can fit this system in order to estimate the traffic condition. So there were two key points that were established for the development of this work. The first is the existence of multiple sources of data coming from traffic systems. So the nature of these measurements is different in general, meaning that it collects a lot of multiple type of variables. And at the same time, those variables that are collected, they present different level of aggregations. So this information that has been widely used in highways can be represented in the map. So in this case, in the Grenoble downtown, we are showing the floating car data, which are measurements collected from GPS sensors, and at the same time we're depicting, for instance, an installation of sensors that has been deployed in the Grenoble downtown in order to measure the number of vehicles crossing at some specific points. So once the state, so the focus in this work was to perform the estimation in this kind of networks, since the highway case has been widely studied, and in addition, since this kind of topologies require more data. Once the estimation of the congestion has been done, one important next step is to add value to this indicator by predicting its evolution. So in this prediction, what we would like to consider is also the dynamic evolution of the traffic, which is established in the data itself. So in this case, we focused in highway networks due to the nature of the system that we are going to, that is an experiment that we have in the lab, and we are going to focus in, and that I'm going to describe later in the presentation. Let me summarize the outline for today. So during the first part of the talk, I'm going to introduce the problem of density and flow reconstruction for urban traffic networks, where the main objective is to perform integration and fusion of multiple sources of data in a model-based approach estimation. Then I will move towards another indicator, which is travel time, and I'm going to describe forecasting techniques for this indicator based on data-driven models. Before concluding this talk, I will present a way we valorize this work in the GTL platform, which is a real-time platform for data traffic data collection. First, what were the motivations of this problem of density reconstruction? So density, which represents the number of vehicles in the space, is an estimation of the congestion. So we selected this indicator because it's a variable that describes the state of the network. But this state cannot be directly measured. So what we regularly collect instead is measurements of speed and flow, which are collected via floating car data in the speed cases and magnetic loop data typically for flow. The objective in this case was using the speed information in order to determine the state of the network via the fundamental diagram. So in fact, by verifying the speeds of each one of the vehicles and aggregated speeds of the vehicles, we were able to reconstruct the state of the network because the mapping is somehow direct. The main problem is that appears is that in some regions of this fundamental diagram, it is not possible to retrieve the density starting from the speeds. So we introduce flow information into the estimation framework, and we also orient this into the estimation framework to tackle the problem, in addition with some assumptions that I'm going to explain later on. We focus this problem into traffic networks. So first, I'm going to briefly describe the road model that we considered. We have considered the Lightning-Williams-Richard model, which was a partial differential equation representing the principle of conservation. In this case, the macroscopic model describes the dynamic evolution of the density, meaning the number of vehicles in the space, as a function of the flow. This flow is also known, the flux function is known as the fundamental diagram, which is a concave representation of that establishes the relationship between flow and density, and determines the propagation of the flow, determines the propagation of the wave of the traffic wave. One particular discrete version of this equation is the LWR model, is the cell transmission model proposed by D'Aganzo, in which the fundamental diagram is linear. Each one of the cells is described by a dynamic equation that establishes the dynamic in terms of a difference between the inflow and the outflow, and the inflow and the outflow can be computed from directly upstream and downstream cells. So this model that can be established for a single road can be extended to multiple roads via the junction model that can establish the relationship between flows in the boundary of the road. And this junction model establishes flow conservation principle between the total incoming flow to the junction and the total outgoing flow from the junction. The solution, in this case, can be established by two rows, and it was established in 2005 by Coquelit, by fixing two roots. The first rule is achieved when we fix the driver's preference matrix, establishing the amount of incoming flow from upstream roads, and the second principle establishing a maximization of the throughput of the network. However, this boundary is bounded, and the demand and supply functions are the functions that appear typically to consider the bounds of the system. For a particular junction, the solution to the problem is found by adding those constraints to the maximization problem, and these constraints can be classified in demand constraints, supply constraints, and altogether they create the subspace for flows which can be uniquely determined for cases in which the number of outgoing flows, outgoing roads is larger or bigger than the number of incoming roads. When we join multiple junctions, we can create a traffic network, and in fact the traffic network evolves with the same discrete model that we see in this equation, where the state contains the densities for each one of the single roads, and we can integrate also the driver's preference matrix into the equation, where the outflow is the solution to the network junction problem in this case, which represents the maximization of the throughput in all the flows inside the network, respecting the boundaries of the flows established by the supply and demand functions. In order to complement this model, we make use of measurements that will fit the problem. So two kinds of measurements were considered in this approach. The first is a set of speed measurements regularly measured from floating car data, which in nature considers aggregated information from vehicles. And the second set of measurements is magnetic loop data, which provides flows at some specific locations. The main characteristic of the first one is the large level of aggregation in time scale, but the good property is that it's generally spatially distributed. Meanwhile, the second one is sparse in the distribution. Both measurements aimed to be combined in order to estimate the density of the system, and at this point it's important to highlight the existing relationship between the speeds and the density, and the challenge-free phase. So on the left side, we consider the outcome from a simulation, which is a microsimulation case in which we measure the relationship between the speeds from vehicles in relationship with the density. This map is not injective in general, in particularly in the free flow region, due to the sparse distribution of points, the scatter points that are in the left part. So this led us to 4 assumptions in the estimation problem we consider. The first one is that we tackle the estimation problem in this way. We consider the first assumption, all the exogenous flows to the network are measured. The second assumption is that all speeds are the speeds given by floater car data are measured everywhere in the network. The third is that for those cells who are in congested state, meaning speeds lower than the free flow, we can establish a pseudo observation of density. And finally, the reconstruction is performed at such speed that the network dynamics evolve smoothly and very slow. And in fact, this estimation problem can be formulated in terms of 2 independent cost functions that penalize the difference between the errors and the estimates. Between the errors, penalize the errors, the difference between the estimates and the measurements. Sorry, we have selected as a quadratic norm in order to measure this difference, and we consider in addition the selection matrix that picks places where there are congestions. All these problems should respect the constraints established by the traffic network, and we finally can propose the following relaxation in order to solve the problem. So the first is that we consider our 2 classic cost functions, measuring the internal outflows on the network and measuring the pseudo observations in the congested cells. In order to recover the flow in those spaces where we don't have measurements, we make use of the steady state equation in the 4th assumption, and moreover, we foster solutions to be within the fundamental diagram, and meaning that these solutions can be constrained to be in an equality space. Finally, in order to complement information to this problem, we add the subspace in which densities exists, and this can be established given the measurement speeds of the system. We have performed a simulation, in this case for a Manhattan network, in which we consider 2x2 intersections with similar parameters in all its roads. In this case, the driver preference matrix was fixed so that 70% of the flow continues straight and 30% turns right, and as a performance measurement, we consider the absolute percentage error. The results show that in the static case, meaning a moment where the network is in equilibrium, the reconstruction can be performed in full similarity. So in the upsize axis, you may see the road ID identification, the road index for each one of for the full cells, and the Y index, the variable comparing the estimated value and the real value. We trace also the evolution in this case dynamically, and we can also see that when the network goes towards equilibrium, we can see how the error decreases and how the estimate reaches the steady state. We observed also the same behavior in flows where the maximum error is about 20% of the capacity of the road at the beginning of the simulation, but then it tends to reduce while the network reaches the equilibrium. Finally, we performed a test to study the sensitivity of the estimation with respect to the noise measurements and uncertainty in the parameters. We consider in this particular case 4 cases. The nominal case I just presented, a case where perturbation existed in the driver's preference matrix, a case where perturbation when noise was added to the measurements of speed and flow, and the results show that in general the flow affects the estimation. The flow is affected by the uncertainties in the matrix R. Meanwhile, the density estimation is more affected by the noise perturbations. In this case. So, some remarks of this problem tells us that the resulting problem was presented in order to reconstruct both variables, which are the flow and the densities, the outgoing flows and the densities. In particularly, the resulting formulation is cast as a quadratic optimization problem, which has nice properties to be studied. The result at the were validated at simulation level, and they were providing satisfactory results in static and dynamic conditions. And finally, we studied the robustness of the method for some particular cases where we introduced uncertainty and parameter variations. And we discovered that in some cases, the parameter variation was affecting the flows, meanwhile the noises were affecting the estimation of density. And in this second part of the talk, we consider the perspectives in terms of proactive tools for traffic systems. So in this research, we consider the travel time as a permanent indicator, but I would like first to highlight which are the main phases of this problem. Not all of them are going to be detailed today, but some of them are going to be explained. So the problem can be split in 4 phases. The first one, a phase in which we collect the data and we compute the indicator we are interested in predicting. Second, for those data who are missing or regularly absent, we need to clean and pre-process this data. Once we have detected clean information, we introduce a clustering algorithm to detect patterns and try to separate out the information. Once the information is obtained, we perform the predictions ahead in multiple steps. And finally, I'm going to explain the validation of these techniques. So, the actual situation is that the density is an indicator which is microscopic and generally is targeted for certain type of users. So nowadays there are a lot of applications that provide specific indicators for trips, and these are very well known, like Waze, Google Maps. These kind of applications have a main issue is that they consider estimation for current time, but the estimation for future time is undefined. In particularly, the computation for future estimations regularly is instantaneous and doesn't perform adaptive conditions to the traffic. So if something changes in the traffic in the future, this estimation is not considered in the application. So we wanted to make use of intrinsic properties existing within the data, and we wanted to use those tools to perform multiple step ahead predictions, which are also known short-term forecasts, in particular of travel time. We wanted also this algorithm to be capable of being extended and deployed in a real-time application. So, in this figure, I'm going to first show the data collection process, and the data collection process can be seen in 3 stages. So, the first step is the collection of event-based data, which are vehicles crossing magnetic sensors. I'm here depicting the profile of a vehicle crossing through 2 sensors in the highway. And the first data that we can collect about this system is a vehicle crossing in the highway, a first level of aggregation is performed when all the events are somehow aggregated in time. A second space occurs at the level of the location, where we can aggregate multiple lane conditions to establish information at a specific point in the highway. And finally, we can perform a mainstream aggregation, meaning that the extraction, the information can be aggregated also in time in order to obtain better behavior of the dynamics of the system and to filter out noise that appears in the data. So the case that we consider in this research was the study of the dynamic travel time, which is a specific way to compute the travel time. This indicator has shown to be more relevant when describing the experience travel time by the user. And let me suppose why. So let's start from position x0 at a time t0, where the user starts its trip. The evolution towards first position we can allow us to update the measurement of speed, and dynamically the user will update the travel time according to the evolution of the dynamics of the system. As a counterpart, the instantaneous travel time can be explained as an instantaneous photo of the speed and in time, meaning that no dynamic condition is considered. In this case, we observed that data, in particularly for the day of September in Grenoble, this is a speed in time and space of the highway, of a highway under study, shows that when we consider the computation of dynamic travel time, in general, it produces higher values when congestion appears. Meanwhile, the instantaneous travel time produce less values, meaning that meanwhile this ITT time would produce less values when the congestion disappears. So the adaptation to this dynamic condition was important in this case. Once we have recovered the indicator, we were interested in analyzing the behavior of patterns in this indicator. So in the figure, we can visualize an historical data set of speeds. Each one of the frames existing in the picture contains a space-time distribution of the speeds for a single day of the month. We can observe somehow some similarities in this data set between the days of the week and the weekends. The fact that data is somehow similar indicates some degree of correlation, and we want to exploit this factor as a potential factor for forecasting. So in order to provide a more accurate indication of this information, we considered a larger data set starting in December 2015, and we analyzed the cross-correlation among the days of the week. The result shows that, in fact, weekdays can be distinguished via this indicator, and strong differences appear in the cross-correlation when analyzing weekdays and weekends. It can be also remarkable that even in between the autocorrelation for the weekdays is higher, and we wanted to look for a tool that was able to extract these features in an automatic way. And the tool that we considered at this point was the k-means algorithm. In this, in order to separate the patterns, we make use of this technique introduced by Lloyd in the 80s. And the main objective is to cluster and to cluster n objects into a specific number of partitions based on a similarity measurement. We selected this approach since the number of partitions can be established, and they are characterized by some specific properties like the centroid and the dispersion. The same principle can be applied and can be extended to time series. And the main considerations at the point were the following. First, let me explain what it does as an algorithm. So starting from endpoints and assigning them and assigning random centroids, we can create partitions by examining the shortest distance from points to centroids. We update the centroids based on this information, and once the centroids are updated, the partitions are updated, and this process continues iteratively until convergence. The main considerations in this algorithm are that the number of partitions is an input and is a parameter that should be fixed. And in this case, the main point was the introduction of dynamic clusterization as a tool to perform the forecast in the day. The reasoning behind that is that all this, the correlation function along the day allows to capture local behaviors around the time window. In particular, we make the use of the algorithm proposed by PAM in 2005 to solve. In this algorithm, a particular function, depending on the total dispersion, is optimized. And before solving this problem, we needed to determine the value of this parameter, which is the number of maximum partitions. So we performed that by introducing, by performing multiple clusterizations to historical data. And by solving in fact, correlating the number of predictions with respect to the dynamic travel time, we've observed that in most of the cases, the number of partitions was between 2 and 4. So, up to now, we have created a way to cluster this information, and we can see its behavior on top of this slide. This approach considers similarities found in the data, and it compresses information in clusters characterized by some centroids and some variance. So it's the top of the slide shows the evolution, for instance, of different clusters along the day. So just to highlight, this approach avoids a priori separation, instead considers some similarities detected among the data, and in addition, the partitions can be obtained in a dynamic way, allowing to establish allow to find similarities in a localized way. The DTT, the number of clusters can be found in an algorithmic and precise way, but moreover it can be trained offline. So we can do a training of the algorithm in an offline way, and the DTT would be clustered according to the Euclidean norm. So let me present now the forecasting algorithm we performed for this case. In this case, the prediction problem is considered as an estimation of the future value of the signal. This is the prediction value. We call forecast multiple, the prediction in multiple steps ahead. And to proceed, we consider the current day information, and we combine it with historical information, in particular represented by clusters, to produce candidate clusters that we called monoclusters. And finally, in order to consider the fact that the day may change from partition while it evolves dynamically, we consider the fusion of multiple forecasts. And then we call this fusion multi-forecast. The approach to extract this information from the data that we have just clusterized is the following. So starting from a set of days, the characterization of a partition is given by a centroid, and its dispersion determined by the days belonging to that cluster. And this information can be collected in the level as a pseudo-observation model. In addition, we can describe the dynamics of the day given by the dynamics, by the trend of the cluster and the dispersion around it. In this case, we consider this model as the process model to be added to the prediction system. The statistical information, in this case, the noises, the characterization of the two noises can be extracted from data via sample estimators. So in the case of the centroids, the sample mean estimator, and in the case of the dispersion, the sample variance estimator. Finally, one of the features for this desired predictor was the combination of current traffic conditions with historical information. So this can be achieved via, and this was actually achieved via the Kalman filter, where the prediction can be established by the process model, and the correction integrates the pseudo-observation, and the updates are modeled by the Kalman gain, which in general consider the variation around the centroids in order to establish the weight of the prediction. So at this point, I can clear out which were the contributions, one of the contributions of this work, and it's the proposal of fusion methods in order to combine those forecasts. And the first principle that we use is a principle based on the error covariance matrix, and the hypothesis is that the error covariance matrix has some information about the predictions, and the prediction of the forecast value can be established as a best linear unbiased estimation of the individual predictions weighted by some by the information contained in the error covariance. We can perform this fusion by solving the problem via the Gauss-Markov theorem, where since the evolution of the Kalman is performed sequentially, it's possible to find also the evolution of the weights in the dynamic way. And this, for more details in this result, we have detailed all the proof in the manuscript. So in order to validate the performance of this method, we have used the GTL platform, which is a platform for collecting data. And we have used data collected at 68 points, in particularly speeds. And as for the moment, it's been 4 years collecting this data. So for the test, we consider 180 days of data of high quality in general. And we have performed a cross-validation test where we consider historical data set is fixed, and we take out one day that we mark as a candidate day. We perform the predictions 25 minutes ahead, in one step ahead, in one step time step predictions for 2 periods on the day. Then this day comes back and performs the computation. Just to signalize, we measured all the errors in terms of the absolute percentage error, which is defined as the difference between the forecasted value and the real measured value. The results for this case were analyzed in terms of the experimental cumulative density distribution, traced for multiple, for different horizons of prediction. So in this case, the APE shows the probability, shows the maximum value of the APE guaranteed to some probability. For the morning case, at most, for instance, 9.21% of the error is achieved with 80% in 80% of the cases, and for a horizon of 15 minutes, and 14.24, around 14% for a horizon of 25 minutes. The same analysis can be done for the afternoon period where errors are around 19 and 27%. And one observation is that the absolute percentage error increases with the prediction horizon, meaning that the farther we go in the horizon, the less precise the information. And in addition, this error can be quantified in terms of travel time as errors in between 1 minute and 7 minutes in the worst case scenario. A second contribution in this work was the fusion. Given the updates that in the previous were done at each time step, these updates didn't consider somehow similarity in a window of time. So a second mechanism proposed to tackle this situation is the hypothesis that the cluster assignment done in a fixed time window can be extended by extracting a similarity measurement in a shorter window of time. And the result of the prediction then can be established as a weighted sum of these similarities in a shorter weighted of time. So let me explain this better. So the similarity can be explained as shown in the figure, where we consider the difference between the level of the cluster and the day in a past window of time, the difference between the trend of the cluster and the trend of the day in a past window of time, and we parameterize this similarity measurement with parameters like a forgetting factor and a parameter that controls the ratio between, or the importance between the level and the trend. The results in terms of experimental cumulative distribution show that the same behavior as the last case, increasing in terms of with respect to future horizon, but in general better with respect to the previous test. For in this case, we can translate these errors as at most 6 minutes in top congestions with a probability of 80%. So, some elements to highlight before from these two approaches. The first one is that the possibility of integrating historical information and partition information was proposed in two algorithms, and both methods can adapt smoothly to the actual traffic condition via the dynamic clustering and the optimal number of clusters, which is a parameter in the algorithm. In both cases, it was found that the prediction error increases with in terms of the horizon window, meaning that for long-term forecasts, the solution tends to degrade, to produce degradation. In general, morning predictions have better accuracy than afternoon predictions due to the distribution of the data, and in particular, this was an observation that we didn't visualize today, but the variance of data sets in between morning and afternoon have big implications, and the number of partitions, of course, have big implications on the accuracy of the method. Both methods were developed by modules, meaning that these methods can be extended to real-time applications. So finally, I'd like to present the deployment of this application, which was the Grenoble Traffic Lab. And these results basically were published in a real-time platform that collects data and provides current traffic conditions and future traffic conditions for a specific highway, the Rocade Sud, in the south of Grenoble. In particularly, 10.5 kilometers, as I explained before, are covered by magnetic sensors. And around the physical collection of data, we have a website that we have created in order to analyze information for multiple users. So we provide information for current status and travel time predictions for general users, for authorities, also by monitoring as a monitoring tool, also as a tool for providing maintenance on the network, and for researchers as a way to integrate and deploy new algorithms on top. So let me show the platform in real life. What we are observing here is the platform that describes some phases. So the first phase is the current status that provides indicators about the network, such as average speed, travel time, and emissions produced by the traffic in actual conditions. A second indicator are the predictions, and in particular, in this case, a user can select a departure point and an arrival point and estimate the prediction in current time, or also go in the past to verify the quality of a particular prediction occurred in the past. So in those cases, the system also suggests the best and the worst options in order to depart and to take the trip. For authorities, we talked more in a future that was more oriented towards the data quality. So authorities are able to check the status of difference of the sensors by inspecting this page in which we describe the failures in the network by checking the conservation flow. In addition, we have detailed also a page in which the data quality can be checked sensor by sensor, and it can be described for some periods in the history, meaning that we can trace the quality of a sensor back in the past up to 6 months. And finally, we can, for instance, observe statistics on the network, and in particular, this allows to study indicators such as travel time, length of the congestion, average speed, total travel distance, in windows of time, of weeks or the month, and check in average how this indicator behaved for particular dates in the past. So let me conclude my talk by reframing a bit the estimation framework that I've presented today. So I've presented a method to reconstruct the simultaneous the flow and estimation, and as a framework to estimate the congestion in a city, and this was established for a urban case. And the nice property of this formulation is that the estimation can be done as a convex quadratic optimization, and the results were proven at simulation level, in which in those cases the reconstruction can be done in a static and in a dynamic way. In addition, we have presented a couple of methods to predict travel time. And the solid performance of both methods was shown in the statistical test. The results of this algorithm were also published in traffic conditions. The integration, so which are the open problems that we envisage for this situation? The first one is the integration of new sources of data. So we have studied a couple of sources of data that are one of the most popular today, but there are additional sources of data that may integrate other kinds of variables. So we consider, for instance, the integration of data GPS traces, which may provide more precise information. So that's aggregation with respect to the floating car data. The information density, which can be the density information, which can be added via camera and sensors. In addition, we consider that also, for instance, one of the parameters, as we saw, was the driver preference matrix influencing the flow estimation, and one of the focus that can lead to a research is the study of this estimation of this parameter, or relaxing the condition in the estimation to this parameter. And moreover, in order to proceed to this direction, there are studies that have been recently proposed in order to constrain the flow optimization problem and to cast the formulation in that direction. At the clustering level, we could study the clustering at a network level in order to forecast predictions at a network level, where we pass from a linear to more complex networks and we cast the problem in new dimensions. So this would suggest how to perform the clustering in space and time, and how to perform the same kind of approach within more complex networks. Finally, a summary of the publications for today. So these are the results. Two results were published in a couple of conferences, and a third result was published in a journal paper, plus all the validation via the platform. Thank you.